So we have the following question. We have 2-point charges. There is charge A and there is charge B. Charge A is negatively charged, so it's a negative charge, and charge B is positively charged. It's a positive charge. I think I'll use a different color. This is better. And we're trying to find the force on a charge positive Q at the origin, so it's positive, and it's at 0, 0. And then later on we have to answer where would we place a point charge positive 5Q such that the net force on the charge at the origin is 0. So I'll start this question off by saying that this is one of the main formulas we need in this question. This formula is known as the Coulomb's law. Coulomb's law just describes the force between any pair of charges. In order to have a force on a charge, the charge has to have a second charge somewhere around it. That's the idea behind Coulomb's law. And basically that's just a constant number. These are the actual charges in units of coulombs with the positive and negative signs, whatever you experience in a question. That is the radius, the distance between these two charges. And then this is basically r hat is just a vector to describe that sometimes the force can be sometimes it can be split over certain coordinate axes. So it can be split. It can have basically I and j components. That's what we mean by the r hat vector. Now that's just, of course, the force vector, and this is the Coulomb's law in vector form. So coming back to this question, first things first, now that I've drawn out the signs of each of the charges, I can kind of draw force vectors between them. So first I'll start with this charge at the origin and the charge B here. Now both of these charges have the same sign, they're positive, so same charges will always repel. Like charges repel. So what that means is that Q will have a force on it that is pointing in this direction from charge B. And charge B would have a force on it from charge Q, positive Q at the origin, pointing that way, but we don't really care about that force. We're focused here only on the charge at the origin. Now we have a negative charge, which is A, and the positive charge again at the origin. Their signs are opposite, so they actually attract. So what that means is that positive Q has a force pointing this way. The force is from the negative charge, charge A. So the fact that charge A and charge Q are on sort of like the horizontal axis shows that we don't have to worry about components to find force A. Neither do we have to worry about finding components for force B, because they're also Q and the charge B are also like on a line on the y-axis. So that's awesome. So notice in this question how they've sort of, in the answer, they've factored out the constant k. They factored out the first charge, and so yeah, I have the two charges also that are factored out. And then the n just means in units of newtons. So I'll start this question by considering the net force, which I already know is pointed this way. Basically, the I component and the j component sort of add and to form a net vector that points this way, in the negative I hat and in the negative j hat direction. So that's like my net force on the charge positive Q in the origin. That's at the origin. So now I'll start with writing the net equation for Coulomb's law, which is going to be the force from charge A plus the force from charge B. Which will become, now the force from charge A is going to be our I hat component. The force from charge B is going to be our J hat component. So basically we have FA I hat plus FB J hat, and I've written this I've written these two forces in their magnitude instead of drawing a vector. The reason why I only need the magnitudes of these forces is because I already kind of know the direction. I know that the force by charge A on the charge at the origin is in the negative I hat direction. So I know that it's going to be negative, and I already wrote I hat. And it's going to be the same thing for charge B. It's in the negative J hat direction. So I know that this is going to be negative as well. Now I need to just find the magnitudes of the forces, because now I've already accounted for the direction, so I don't have to worry about the vector form anymore. I've already written this equation in vector form using unit vectors and the directions of each of these vectors, of each of these forces, sorry. Now the main thing I have to do is I have to find basically the radius over here, as in the distance between charge A and the charge at the origin, and also the distance between charge B and the charge at the origin. So I'll name the distance between charge A and the charge at the origin as RA, and I'll call this RB, the distance between charge B and the charge at the origin. Now RA is easy to find because we're going from 0, we're going -1, -2, -3. Remember that this is a distance, so it's just 3 meters instead of -3, it's just +3. RB is also going to be so I made a mistake there. I meant this. This is the radius, this is the distance between charge B and the charge at the origin, which is going to be +2 meters. Distances are always positive. Now what I'll do is I'll sort of write out the equations. So we have K, and charge A was -4Q, so I'll make this a positive sign, and I'll move the 4 here, and it's capital Q and positive small q over RA, which was 3 meters. And my charge B is positive 3Q, so that's going to be negative, and then 3 big Q small q from the charge at the origin divided by RB, which is 2 meters, I believe. Yes, so 2. Now this would be the answer, except that I have a positive sign here where I should be having a negative sign. So I already accounted for the signs of the force vector. So basically in the Coulomb's law equation, first of all, you have a direction which can be negative, but also even when you're solving for the magnitude of the force, okay, So that's actually my problem. The reason I have a positive sign down there is because I already accounted for the directions of the forces. So now, at this point, I was only solving for magnitudes, which means that my equation actually looked like this, in magnitude form. It looked like this. So if I get a negative sign from any of these charges, it would automatically cancel out because of the absolute value here. So I would just get like the actual numbers, not the signs. And so that was a problem here. I plugged in -4 when I didn't have to do that. That was a mistake. So actually the sign here would be negative. Basically, again, to repeat one more time so that you've understood, I started with this equation in vector form, right? Now, when I kind of just drew out the vectors because that was the easiest way to figure out the direction of the net force vector on the charge at the origin, which was negative I hat, negative j hat, and then some number for each of those components. So I already know that these are in, like, the direction of the force vector. I already know that it's negative in the I hat direction, negative in the j hat direction. So that's great. I've accounted for the direction. So at this point, I'm just solving for the magnitudes of the forces, which means that I apply an absolute value on this equation, which automatically makes any negative charge positive. And I forgot my unit vectors here. So basically this now there's a mistake I've made with my Coulomb's law equation. I hope some of you have realized it's supposed to be r squared. Because of that, this 3 is actually going to get squared, and this 2 down here is also going to get squared. 3 squared is 9, and 2 squared is 4. So now I get the correct answer, -4/9 and -3/4. Basically, what these guys have done here is the following. I'll write it out for you. We have two terms here, and what's common among all of these terms is the fact that are these three variables: k, big Q, small q, k, big Q, small q. So we've just factored them out. I know I'm being a bit redundant, but it's just so that you could understand. So that's j hat, and they've just factored out k, big Q, small q, and they've written it like that. That's all they did. So now that we're good with those things, let's move on to part B. So now that we've finished part A, we need to continue with part B. We put the positive 5Q charge over here in the third quadrant, and that's because two positive charges repel each other. And if I'm thinking about the force that this positive 5Q charge exerts on the charge at the origin, then it's going to repel in this direction. So this is the correct place to put the positive 5Q charge so that these two vectors can cancel and you can get a new net force of 0. Now, the first thing we're going to do is find the radius, the distance between this charge and this charge at the origin, the positive 5Q charge and the charge at the origin, which I'll call R5. To do that, we start with the following. The first thing we need to do is we need to find the magnitude of the net force from part A, which is going to be simple. It's going to be the square root of the x and y components squared. So the x component is -4/9, and we leave that factored out. We don't really care about the k, big Q, small q in this type of question. But in reality, what actually happens is when we factor that out, we just leave it on the side, like here. Small k, k, big Q, small q, sorry. And so we get a net force, the magnitude of the net force to be square root of we get 0.8718 k big Q small q. So that's great. That's the magnitude of the net force from part A. And we want that to be equal to the magnitude of the net force. No, sorry. We want it to be equal to the magnitude of the force of the positive 5q charge on the charge at the origin. So we're going to use Coulomb's law K, and then positive 5q, so we're going to put a 5 here, big Q, and then small q, because the force is going to be between the positive small q charge and the positive 5 big Q charge over r squared, which I called r5, so it's r5 squared, and it's a magnitude. So when I look at both sides of this equation, basically I'm setting the two equations equal to each other. So the net force from part A is equal to the force by the positive 5 big Q charge on the charge at the origin. So these two are common terms, K, big Q, small q, so they cancel. Then I rearrange for R5. So we have 5 divided by 0.8718 square root. So we get a value of 2.395 meters for the distance. So that's great. Now I'm going to erase what I have at the top here. My font is a bit too large. Now R5 is the distance between the charge at the origin and the positive 5q charge. Now we need to technically find the displacement, so like the vector, right? So we need to find this angle in order to do that. So we'll be using the net force from part A and using the tangent identity we can find the angle here. Angle theta. And then once we have the angle theta, we can simply find the x and y components of the actual displacement. So what I'm saying is that tangent theta is equal to y over x, because opposite over adjacent. So opposite over adjacent. And so these are like the actual components of the force, the net force from part A. So opposite over adjacent. And then I do tan inverse to get the actual answer. Now, one thing to keep in mind, let me find the answer and then I'll explain. I got an angle of 59.34 degrees. Let's say 59.35. I'll round that up. So, one thing to keep in mind about this angle is that we got a positive answer, but the main thing we need to keep in mind is that we're actually sitting below the x-axis. So when we're sitting below the x-axis in this direction, we say it's actually negative. Again, if I wanted the angle to be positive, I would have to add 180 degrees to it because I have to start from the positive x-axis. In general, when we measure angles, we always want to start from the positive x-axis and then go this way. So I would be doing a semicircle, which is 180 degrees, plus the angle of 59.35 that I found here in this region. So right now, what I'm saying is instead of going from the positive x-axis, we can just go from the negative x-axis and just say that the angle is negative 59.35 degrees, and that negative sign accounts for the fact that we're only looking at this angle and we're starting downwards from the x-axis. So we have, what I'm trying to say is that that's why we have a negative sign here, though it doesn't come from the equation, the values themselves. So I'll be doing some erasing here. So now we're closer. We have our angle. Now we just need to find the components of the displacement vector using the magnitude of the displacement vector, which is the distance between the charge at the origin and the positive 5 big Q charge. And then we have the angle theta as well to help with that. To find R5, we have R5 here, that's the distance. And now we just need to find its x and y components. We know they're going to be negative. So here's the x component, here's that angle, which is negative, and that's the y component. I'll do adjacent over hypotenuse, which is Ka, to R5 cos theta to give us the x component. And I'll do R5 sine theta to give us the y component, because that is so katoa, so which is opposite over hypotenuse. Opposite to this angle over that hypotenuse. I'll plug these values in for you. I'll write them down, that's what I'm trying to say, so that you can understand. So we're doing 2.395 meters times cosine of negative 59.35. And then 2.395 meters times sine of negative 59.35 degrees. So that gives us 1.22 meters on the x axis, and we're getting a positive answer with a negative angle. That's interesting. And then we have a negative answer for the y, so that's good. Negative 2.06 meters. Now, I don't know why we didn't get a negative answer here for the cosine. The way we've done the problem is correct. So if you follow through with your own question and its values, you'll definitely get the right magnitude of the answer for the x component. It's just that we need to keep in mind that the positive 5k charge is indeed in the third quadrant, which means that the x component has to be negative and the y component also has to be negative. So I don't know why our calculations didn't give us a negative sign here, but there is supposed to be a negative sign. So this would be the correct answer. So again, if you're solving the same question but with different values, if you follow the steps that I did, you'll get the right answer. But just keep in mind that don't forget a negative sign for the x here. So yeah, we get negative 1.22 and negative 2.06. So that's good. I hope this helps, and have a good day.